So I've gotten two different practice quizzes, one from Adrianna and one from Caroline. We're going to get started with Adrianna's first. In the first question, you can see that I've changed 12 centimeters to meters. The reason for this is not because it's bad to have it as centimeters and make us switch units. I just want to kind of simplify it for this practice problem, but that would be a good thing that might show up on the quiz this Friday. So if we're trying to find the mechanical advantage of a wheel and axle, we divide the radius of the wheel, which is 12, by the radius of the axle, which is 3. So that gives us a mechanical advantage of 4. Okay? If a ramp is 1 meter, 0.25 meters high, and has a slope that is 7 meters long, what is the mechanical advantage? I'm assuming that what this was intended to be was 1.25 meters. So we'll base it off of that and not, 1 meter or 0.25 or something, but it was supposed to be 1.25 meters. So in this case, you divide the slope by the height. So that would be 7 by 1.25. And that equals 7 divided by 1.25, 5.6. That would be the mechanical advantage. The length of a knife is 6 centimeters and its greatest thickness is 1.5 centimeters. What's the mechanical advantage? Again, you divide length by thickness, so 6 by 1.5. 1.5 fits in 4 times, and there you have it. How much power does it take to raise your 2 kilogram hand 1 meter 10 times during a science block? That's 80 minutes. So first thing we need to figure out force, which if we've got 2 kilograms, that's the mass, we multiply it by 10 meters per second, and we've got a force of 20 newtons. We're moving, the distance will be 1 meter. We're doing this a total of 10 times, and if we're looking at time, it's 80 minutes, so if we multiply that to get into seconds, by 60, we're left with 4,800 seconds. So now we can set it up. Work equals force times distance. Work is what we're solving for. Force is 20 times 1. Work is going to be 20. Now we're doing it 10 times, so it will actually equal 200. So power is work divided by time, so that will be power equals 200 divided by 4,800, and power is equal to 0.0416 watts. I'm going to erase that and just make it a little bit clearer. 0.0416. All right. Which compound machine would you expect to have the lowest mechanical efficiency? A can opener or a pair of scissors? So a pair of scissors is really just 2 levers or 2 wedges acting together, kind of on a movable lever there. And then we've got the can opener, but a can opener, as you remember from the notes, has about 4 or 5 different mechanical machines, or simple machines rather, inside of it. So the greater the number of simple machines, the less mechanical efficiency it has. So that means that a can opener would win this one in having the lowest mechanical efficiency. Thank you, Adrianna. Coming over here to Caroline, she first says name the 6 type of simple machines. So that would be a lever. I just can't fit it all going down like that. A pulley, inclined plane, wedge, wheel and axle, and a screw. What I would like you to know about each of those is probably have some information about an example. Remember, I'm just going to remind you of this. You want an example. Whoa, Haley. An example, as well as to know the mechanical advantage, as well as to know the direction for at least levers and pulleys. Okay. The slope of a ramp is 16 meters long and the ramp is 6 meters high. What is the mechanical advantage? So we figure this out in Adrianna's. We take 16 divided by 6, length by height, and that's going to equal 2.67. A wheelchair ramp is 87 meters long and 8 meters high. What's the mechanical advantage? 87 divided by 8, and we're left with 10.875. The radius of a wheel and axle is 122 meters, and the radius of the axle is 2 meters. 122 divided by 2, and we are left with 40.67. What is a second-class lever? How can a second-class lever be useful? Give examples of a first, second, and third-class lever. Great question, would be worth lots of points. So a second-class lever would look something like this. Fulcrum, load, input. So your definition of a second-class lever would be that that the load is in between the fulcrum and the input, meaning you picking it up. If we imagine this as, if we want an example of this, it would be a wheelbarrow. So these are useful for carrying heavy objects. Right? Wheelbarrow can transport things all over campus. The mechanical advantage of this will be greater than 1. So an example of a first, we could have a levering a rock out of a hole. Obviously it's a lever, levering the rock out of the hole. We could have a scale, or we could have, like a rowboat. The second would be right over here. And the third class lever, an example could be the bicep curl or the hammer. Number 6, does a third class lever change the direction of a force? Circle 1. No, it does not. The third class lever, meaning the bicep curl or the hammer, you put the force in the same direction as the output force. The power that it takes to lift a puppy is 1372 watts. If he did 4 joules of work, how much time did it take him? Great question. So we have power, we have work, and we don't have time. Okay, so remember, I always like setting up this stuff on the side here just to help me organize my thoughts. So if power is work over time, that will be 1372 is 4 over t. Multiply both sides by t, that cancels out. So now we're left with 1372 t equals 4. Divide both sides by 1372, that cancels out, and that equals a very small number, 0.0029 seconds. That makes sense because you're only doing 4 joules of work with 4 joules of work and so much power, you must have done it very, very quickly. Small amount of work with a lot of power, you had to do it fast. Number 8, when playing a game of basketball for 4 hours, I'm actually going to give us some more space here. That's a good question. When playing a game of baseball for 4 hours, the girl lifts up her water bottle a total of 204 times to take a sip of water during the game. She wants to stay hydrated. If the water bottle has a mass of 4 kilograms, her arm has a mass of 2 kilograms, and she raises her arm a distance of 2 meters, how much power did she use? All right. So first, let's start with time, because that's the first thing she gives us. So time is going to be 4 hours. If we multiply that by 60 minutes and by 60 seconds, that will get us to 14,400 seconds. We're doing this 204 times. We've got, if we're trying to find force, we've got 2 forces to deal with. We've got the 4 kilogram force of her water bottle and the 2 kilogram mass of her arm. In both cases, she's lifting her arm and the water bottle up, meaning it's fighting the force of gravity, meaning it's force due to gravity, therefore weight, therefore they both count. So multiply both of these by 10, and that will give us 60 newtons of force. The distance is 2 meters, and we are solving for power. So if we have work equals force times distance, work will equal 60 newtons times 2 meters. So the work will equal 120 joules. Okay, so this is step 1. Now, then we know that we need to find total work, meaning 120 times 204, because she did it 204 times. That gives us a total work of 20 4,480 joules. She did a lot of work. Now, to calculate her power, though, power is work divided by time. Power will equal 24,480 divided by 14,400. So close that those could have gone into each other. Nice and easily. Power will equal 1.7 watts. This right here is your final answer. That's the power that she used to lift her arm all those 204 times in 4 hours. Not all that much power, which makes sense. You're just lifting your arm in the water bottle, but doing it 204 times across 4 hours, that much power, significant amount of work. Final question. Harold uses 104 joules of work to lift a weight for 45 seconds. How much power did he do, or did he use? Okay, so first, I'm assuming that this question is not saying that Harold held the weight up for 45 seconds, right? Which would mean that there was zero work done. Since she tells us how much work, I'm assuming she's actually talking about lifting that weight up. This comes from a question that I had on the quiz where I worded it like this, and it wasn't worded very clearly. So that's really my fault. Power is work over time. So that's 104 joules divided by 45, which gives us an answer of 2.31 watts.